Welcome back to the deep dive. It is Wednesday, February 25, 2026. And I have spent the last 48 hours just completely buried in a stack of reports that is, quite frankly, a little intimidating.
Oh, I bet.
Yeah, we have everything here, from the latest planetary radio archives to the raw data dumps from Space News Today. And if I had to put a headline on this specific moment in planetary science, I'd say we're living through the golden age of the reality check.
That is a very diplomatic way of putting it, I think. I might call it the golden age of complication.
Complication is right, because on one hand, we're rewriting the history books, literally rewriting them. We're changing the timeline of Earth's water. We're finding galaxies that just shouldn't exist. And, we're mapping the actual edge of our solar system. But then on the other hand,
We have leaks.
we have leaks, we have delays, we have physics telling us that our favorite moons might just be dead rocks.
Right, it's the friction between our romantic view of space exploration and the harsh engineering and geological reality. We have this narrative in our heads of the great human adventure, right? Like Captain Kirk warping to the next planet, finding easy-to-access water and habitable worlds. But the reality, as we're seeing in all this research you brought today, is that the universe is messy. It's often hostile. And it definitely doesn't give up its secrets easily.
Exactly. And so that is our mission today. We are going to synthesize this massive stack of updates for you into one coherent picture. It's basically a detective story. We've got clues hiding in Apollo-era moon dust, missing stars in distant galaxies, and a very stubborn helium leak down in Florida.
And like any good detective story, we really have to start with the origin, the scene of the crime, if you will.
Let's start with the moon, because for a supposedly dead rock, it is suddenly the most interesting place in the solar system again. We have this fascinating report featuring Tony Gargano from the Lunar and Planetary Institute. And the core question his team is tackling is one that I think most of us just stopped thinking about after grade school. Where did Earth's water actually come from?
It's the most fundamental question for our existence. You look at a globe, it's blue. We are the water planet. But scientifically speaking, the origin of that water is a massive ongoing debate. Did it bubble up from the mantle? Did it arrive on comets? Did asteroids bring it?
You'd think we would know this by 2026, honestly. I mean, we've been studying geology for centuries.
You would think so. But the big problem there is Earth itself. Earth is a terrible place to study Earth's history.
Because it recycles everything.
Exactly. We're just too active. We have plate tectonics subducting crust, constantly sucking it down into the mantle and melting it. We have rain eroding the mountains. We have biology changing the chemistry of the atmosphere of the soil. Earth is constantly erasing its own hard drive. So if you want to know what happened 4.5 billion years ago, you cannot look at Earth. The data is just gone.
Enter the moon, the witness plate. I love that term so much.
It's the perfect description. The moon has just been sitting there, largely biologically and geologically inert, for billions of years. It shares our exact space in the solar system. It's been collecting the exact same debris, the same solar wind, the same impacts as Earth. But unlike Earth, it kept the receipts, didn't recycle them.
So Tony Gargano and his team went back into the vault. They pulled out lunar regolith, literally moon dust collected during the Apollo missions in the early 70s. And this is what blows my mind. We have had this dust for over 50 years. What exactly can a jar of dust from 1972 tell us about the oceans today that we couldn't figure out back in 1972?
Well, it comes down to technology and isotopes. We have analytical instruments now that are exponentially more sensitive than anything they had in the Apollo era. This is chemical fingerprinting. Specifically, they're looking at the hydrogen isotopes, which is the ratio of deuterium to normal hydrogen. This is critical because different sources of water in the solar system have completely different flavors of hydrogen.
Flavors. Unpack that a bit.
Think of it like a brand label. Comets, which formed way out in the deep freeze of the outer solar system, usually have a much heavier ratio. They have a lot more deuterium. Asteroids, specifically the ones in the main belt much closer to us, have a lighter ratio. So if Earth's oceans were filled by icy comets raining down on us, our water would be heavy. It would match that comet brand.
Okay, so if we find heavy water signatures on the moon, it means comets bombarded both of us.
Precisely. But that is not what Gargano found. In the lunar samples, which serve as this perfect proxy for what was hitting the Earth-Moon system billions of years ago, the isotopic signature does not match comets at all. It matches carbonaceous chondrites.
Carbonaceous chondrites. That sounds like a heavy metal band, but those are meteorites, right?
Yes, it's a specific class of stony meteorites that are rich in water and organic compounds. They originate from the asteroid belt, not the deep, frozen outer solar system where the comets live. The findings from this lunar dust strongly suggest that the vast majority of our water was delivered by these asteroids, and very early in the solar system's history.
See, this completely changes the narrative I had in my head. I always pictured the late heavy bombardment as the super dramatic rain of comets turning Earth into a giant swimming pool. But you're saying it was just wet rocks?
Wet rocks. And this matters immensely for the timeline of habitability. If water arrived via asteroids, it implies that the ingredients for life, the water and the organics, were delivered together, and they were delivered early on. It basically sets the clock for life on Earth, starting much sooner than if we had to wait around for a late comet bombardment.
So in a way, understanding the moon is the only way to really understand the timeline of us. We are looking at the moon to see our own baby pictures.
That's the beauty of planetary science. You can't understand Earth in total isolation. We're part of a system, and that system shares a history.
Speaking of the system, let's talk about our current efforts to get back there, the Artemis program. We have updates from Space News today and some really great interviews from Planetary Radio with the people actually designing the science for these missions. And I want to focus on the people first because the rockets always get the glory, but the science is the point.
Right, Kelsey Young and Noah Petro. This represents a really critical shift in mentality for the space agency.
Kelsey is the Artemis Science Flight Operations Lead, and Noah is the Artemis III project scientist. And they made a point in their interview that really stuck with me. They said they are actively training the astronauts to observe like geologists.
Which is a huge departure from the 1960s.
Huge. The Apollo guys were test pilots. They were brilliant engineers and pilots, absolutely the best of the best. But with the exception of Harrison Schmitt on Apollo 17, they weren't scientists. They were trained to fly the machine and just survive.
And frankly, that was the right choice for the 60s, because the machine was highly experimental and incredibly dangerous. Just getting there and getting back alive was the primary mission. But now, the goal is sustained presence and actual science. Noah Petro made this great point. You can have the best robotic sensors in the universe, but the most powerful scientific instrument is still the human eye connected to a human brain. A robot sees data, but a human sees context.
So what does that training actually look like? Are they just sitting in a classroom looking at pictures of rocks?
Oh no, they are out in the field. They go out to Iceland, they go to the Arizona craters. They are learning to read a landscape. A human can look at a field of gray dust and say, wait, that rock over there has a completely different texture. It looks like it was thrown here from a different crater, which means it might be a sample of the deep crust. A rover might just roll right past that because it wasn't programmed to look for it.
So for Artemis II, which is just the orbital mission, they aren't actually landing. But they have this thing called the Lunar Observations and Imaging Campaign. It sounds very fancy, but isn't it essentially just taking photos out the window?
It's reconnaissance, but it's highly targeted reconnaissance.
Yeah.
They aren't just snapping holiday photos of craters to throw up online. They are being trained to identify specific geological features, things like impact melts or stratigraphic layering in the crater walls, things that will directly inform exactly where Artemis III eventually lands. They are essentially scouting the landing zone for the next team.
And Artemis III is heading to the South Pole. We hear South Pole constantly in the press now. It's the big buzzword. Why? Is it really just because we haven't been there yet?
That's a small part of it, but it's really about two major things: volatiles and geology. The South Pole has these permanently shadowed regions. These are craters where sunlight hasn't touched the floor in literally billions of years. That is where the water ice is hiding. That's the resource for fuel and life support.
Okay, so that's the gas station argument. If there's ice, we can make rocket fuel.
Right. But geologically, the South Pole is also distinct. It's ancient highlands terrain, very different from the Mare, which are those dark, flat lava plains where all the Apollo missions landed. This is the rugged, heavily beaten-up crust of the moon. It gives us a completely different slice of history. If Apollo gave us the story of the lava flows, Artemis is going to give us the story of the ancient crust formation.
So the science is ready, the training is happening, but then we hit the golden age of reality again, the delay.
Rollback.
Yeah. According to reports from just this week, February 2026, the Artemis II stack, the massive Space Launch System rocket, has been rolled back to the vehicle assembly building. And the culprit, helium.
It is always the smallest molecule that causes the absolute biggest headaches.
A helium flow issue in the upper stage. To the average person listening, a helium leak sounds like a kid's birthday party problem.
Oh no.
With the balloons are sagging, why is this stopping a multi-billion-dollar lunar mission?
In rocketry, helium is absolutely critical. It's used to pressurize the fuel tanks. Think of a plastic soda bottle. If you suck the liquid out, the sides crinkle and collapse in on themselves unless you let air back in. In a rocket, as you burn fuel, the tank empties very fast. If you don't fill that empty space with something, the pressure drops and the engines starve. Or worse, the structural integrity of the tank fails and it just collapses. You use helium because it's inert, it won't explode, and it stays a gas even at super cold cryogenic temperatures.
So a leak means you lose that pressure.
The leak means you cannot guarantee the engine will keep running. And on a mission with humans on board, where that upper stage engine is literally your only way home from the moon, maybe isn't good enough. You cannot launch.
The human cost of this delay really struck me in the reports. I read that the crew commander, Reed Wiseman, and the rest of the team were actually already in quarantine. They were deep in that pre-flight mindset. They had essentially said their goodbyes to their families, and then release. Go home, guys. We have to fix a valve.
It's incredible mental whiplash. You build yourself up psychologically for the most dangerous thing a human being can do. You isolate yourself, you focus completely, and then the adrenaline just dumps. But I think this really highlights the difference between the space race of the Cold War and today. In the 60s, there was a tolerance for risk that simply does not exist now. NASA's mantra today is very much, we fly when we are ready.
Even if China is breathing down our necks. Because we know they are aiming for the moon too, and they are moving fast.
That is the tension, absolutely. We'll get to China's rapid progress later in the deep dive. But if NASA rushes Artemis II and something catastrophic happens, the program is dead, not just delayed, canceled. The political will simply won't survive a disaster. So the delay is painful, it pushes the launch window from March to April or even later, and it's expensive, but it's the only acceptable move.
It's a sober reminder, space is hard. But let's zoom out a bit. If the moon is giving us a hard time, the outer solar system is giving us a full-blown existential crisis. Let's move to segment 2 and talk about ocean worlds.
The quiet seafloor hypothesis. This is a really tough one for the optimists out there.
It really is. For years, Europa Jupiter's icy moon has been the absolute darling of astrobiology. We look at that cracked ice on the surface, we know for a fact there's a global liquid ocean underneath it. And we assumed, or maybe we just really hoped, that the seafloor down there is teeming with hydrothermal vents. We picture the mid-Atlantic ridge on Earth with black smokers and tube worms and crabs everywhere.
Exactly. We used Earth as the default model. On Earth, plate tectonics drive water down into the crust, magma heats it up, and it shoots back up rich in minerals. That creates chemical energy. Life loves chemical energy. It's basically free food down in the dark.
But Paul Byrne from Washington University in St. Louis is basically pouring cold water on that entire idea. He was on Planetary Radio explaining his new study. What is his argument here?
It comes down to rock mechanics. His team modeled the physical strength of the rock on Europa's seafloor. You have to remember, gravity is very different there, and the pressure from the miles of water above is immense. Their study suggests that the rock at the very bottom of Europa's ocean might just be too strong to crack deeply.
Too strong to crack, so the water just sits on top of solid stone.
Exactly. To get a hydrothermal vent, you need the water to percolate deep down into the crust, kilometers down, to reach the hot stuff. If the rock is compressed and sealed tight, the water just can't get in to be heated.
So it's not a churning, chemically active soup, it's just a stagnant bucket of water.
Stagnant is a bit harsh, but yes, it might be chemically isolated. Without that interaction, what geologists call serpentinization, where water changes the rock and releases hydrogen, you simply don't have fuel for life. You might have an incredible, vast global ocean that is just completely sterile.
That is honestly depressing. We've spent billions planning the Europa Clipper mission to go look at this place.
It's a recalibration of expectations, for sure. But here's the twist. While Europa might be completely quiet, Saturn's moon, Enceladus, is screaming at us.
Enceladus is the little one that actively sprays water out into space, right?
Yes. And we know for an absolute fact that Enceladus has vents. The Cassini probe actually flew right through those plumes years ago and detected something very specific in the water: silica nanoparticles.
Silica nanoparticles. That sounds highly technical. What does finding that actually prove?
The only way to make silica grains of that specific tiny size is to have liquid water touching rock at temperatures of at least 90 degrees Celsius. It is a smoking gun. Enceladus is geologically alive, its core is hot, its water is actively interacting with the rock, and it's venting that cooked material straight out into space.
So Europa is the big lockdown fortress, and Enceladus is the active, messy little laboratory.
It seems that way. It teaches us that ocean world is a very broad category. Just because you find liquid water doesn't mean you automatically have life. You need the energy, you need that spark.
Well, while we're out at Saturn, we really have to touch on the violence of that system. Space News Today had a piece on the origins of Titan and the rings. I feel like every few years, the estimated age of Saturn's rings changes completely.
It does fluctuate.
Yeah.
But the evidence is really converging on them being young. The latest theories suggest that Titan, Saturn's massive, smoggy moon, might actually be a Frankenstein's monster.
Yeah.
It might have formed from the direct collision of two older, pre-existing moons.
A moon merger. That sounds incredibly catastrophic.
It would have been an absolute apocalypse in the Saturn system, a massive high-speed collision.
Yeah.
And the debris from that era, or perhaps even a third moon that got shredded by tidal forces during all this chaos, became the rings.
And this happened relatively recently.
In geological terms, yes, maybe 100 million years ago. To put that in perspective for you, dinosaurs were walking around on Earth when this happened. If a T-Rex had a decent telescope, he would have looked up at Saturn and seen nothing. No rings. Maybe just a messy cloud of dust starting to organize itself.
That is such a wild thought. We tend to think of the planets as these eternal, static paintings in the sky. But they're not.
No, not at all. We're just looking at a single frame in a very long movie. Saturn's rings are a temporary feature. They are stunningly beautiful, but they are just the aftermath of a disaster, and eventually they will rain down into the planet and completely disappear.
Okay, let's bring it back in closer to the sun. Segment 3, the inner planets. We have massive updates on Venus and Mars. And Venus is the planet that just keeps on giving, even though we haven't sent a successful new lander to the surface in decades.
The Magellan data. It's the gift that keeps on giving. Magellan mapped Venus with radar back in the early 90s, and we are still finding entirely new things in those old files today because our computer processing power is just so much better now.
The big headline here is lava tubes, but not just any lava tubes.
Monster tubes. On Earth, a lava tube, which is basically a tunnel left behind by flowing lava that crusted over on top, might be 10 or 15 meters wide. You can walk through it comfortably. But the new analysis of the Venusian radar data suggests tubes up to a kilometer wide.
A kilometer. You could fly a 747 through that. You could fit the Burj Khalifa inside there sideways.
You could build an entire city in it. And that is exactly why this is so exciting for the space futurists.
Because the surface of Venus is literal hell.
It is the definition of hell. 460 degrees Celsius, 90 atmospheres of crushing pressure. It rains sulfuric acid. You cannot live there. Even heavily armored robots die there in a matter of hours. But underground, inside a massive lava tube.
What changes down there?
You're completely shielded from the solar radiation. You are protected from the acid rain. The temperature would still be incredibly high, sure, but it would be stable. It's what we call thermal inertia. If you can insulate your habitat, a deep lava tube is realistically the only place on Venus where you could arguably survive.
It's straight out of a sci-fi novel. Subterranean Venusian colonies, just living in the empty veins of the planet.
It's a long shot, obviously, but knowing they exist changes how we plan future exploration. If we send a rover or a floating drone in the future, maybe we don't aim for the flat plains. Maybe we aim for a skylight, a collapsed roof of one of these tubes, and try to peek inside.
Moving one planet over to Mars, there's so much happening on Mars right now. We absolutely have to talk about Escapade. This launched recently on Blue Origin's New Glenn rocket, which honestly is a headline in itself.
It is. Seeing New Glenn finally flying real science missions is a huge validation for the private space sector. But the science of Escapade is fascinating. It's part of the Simplex program. Small, low-cost, and it's a twin mission. 2 small satellites.
What exactly are they looking for?
They are hunting the ghost of Mars's atmosphere. We know Mars used to be wet and warm. It had a thick atmosphere. Now it's incredibly thin and freezing cold. Where did all the air go?
It escaped to space?
Right. But how, exactly? Mars has these weird, patchy magnetic fields stuck in its crust. They're remnants of a global field that died billions of years ago. Escapade is going to fly right through these magnetic patches and watch how the solar wind interacts with them. It's studying the sputtering process, literally watching individual atoms being violently knocked out of the atmosphere by solar particles.
Wow, is watching a planet bleed to death.
Slowly, yes. And we are learning that the Martian weather plays a huge role in this bleed. Space News Today reported on these global dust storms.
The death pump.
Exactly. We used to think water loss was just a slow, steady trickle. But it turns out when Mars has those massive global dust storms, the ones that cover the entire planet, they act like a giant pump. They heat up the atmosphere, causing it to physically expand, and they loft water vapor way, way up high.
Higher than it should normally be.
Much higher, up to where the harsh UV radiation from the sun can hit it and physically break the water molecules apart. Once the hydrogen is loose, it's so light that it just escapes Martian gravity entirely. So dust storm basically serves up the planet's remaining water on a silver platter to the solar wind to be stripped away.
So Mars isn't just losing water passively over time. It's actively throwing it away every time there's a major storm.
Which implies that Mars might have dried out much faster and in much more dramatic bursts than we previously modeled.
Real quick on Mars rovers, we also saw a note that Perseverance has gained the ability to locate itself with GPS-like precision without any Earth assistance, which is crazy to think about.
It's pure autonomy. It speeds up the driving immensely because it doesn't have to phone home to ask where it is.
And while the atmosphere is leaving and the rovers are driving themselves, we're still fiercely debating how to put humans there. But the tone of that conversation is really shifting. We had the Mars Society convention recently.
Always a very passionate group of people.
Very. You have the diehards like Robert Zubrin yelling about Mars Direct. Just go, use the science, figure the rest out later. But then you have this new wave of realism stepping in. Tiffany Vora was talking about synthetic biology.
Which is equal parts terrifying and brilliant.
Engineered microbes.
It's the only sustainable way. You can't ship vitamin C and antibiotics to Mars forever. They degrade in transit. You need to print them biologically on site. You need to engineer microbes that can eat toxic Martian regolith and poop out useful plastics or farmable soil. It's biomanufacturing. Oh, and Melody Yarshar talking about 3D printed habitats using that same dirt.
But even with all that incredible tech and development, the pivot is happening. Elon Musk, Mr. Mars himself, is signaling a major shift toward prioritizing a moon base first.
It's the brutal logistics of it all. Mars windows only open every 26 months. The trip is 9 months long. If you forget your toothbrush, you're out of luck for 2 solid years. The moon is 3 days away. If we want to actually build a robust space economy, you have to build the local harbor before you cross the deep ocean. The moon is the harbor.
It really feels like the romantic phase of Mars colonization is finally meeting the engineering phase, and the engineers are winning.
The engineers always win in the end. Physics is undefeated.
Let's go further out. Segment 4, the edge of the system and beyond, Voyager. The little probe that absolutely won't quit.
Yeah. Linda Spilker, the project scientist, gave a fantastic update on this. Voyager is officially out in the interstellar medium. It has pushed past the protective bubble of our solar system.
And it turns out the edge of the solar system isn't just a clean, quiet line.
No, it's a mess. It's incredibly turbulent. The solar wind piles up out there, creating these massive shock waves as it crashes into the gas between the stars. It's not a gentle fade out into the black, it's a violent crash barrier.
And to map this barrier better, we have the IMP mission launching soon, the Interstellar Mapping and Acceleration Probe, sitting out at the L1 Lagrange point. This thing is so cool because it uses energetic neutral atoms.
It is.
Break that down for us. What exactly is an energetic neutral atom?
Okay, imagine a charged particle from the solar wind moving super fast. Outward hits a cold neutral atom floating in interstellar space. They crash, and they can trade an electron. Suddenly, that fast-moving solar particle becomes electrically neutral. Because it's neutral now, it's no longer affected by the complex magnetic fields out there. It travels in a perfectly straight line.
So it creates this straight line ray that points exactly back to where the collision happened.
Exactly. IMAP acts like a catcher's mitt for these atoms. By tracing their straight paths back, it can literally paint a 3D picture of the invisible boundary where they were created. It's like using sonar to see the edge of the solar system's bubble.
Why does the average person listening to this on their morning commute care about the edge of the heliosphere?
Because it's our shield. That bubble blocks a massive amount of lethal galactic cosmic radiation. If that bubble didn't exist, or if it radically changes shape as we move through the galaxy, the radiation environment right here on Earth changes. Understanding that shield is understanding why we aren't being completely fried by the galaxy.
Now, speaking of things we literally can't see, let's talk about the dark matter galaxy. This broke my brain a little bit reading the prep. CDG2.
Right, in the Perseus cluster. 300 million light years away.
It's a galaxy, but it has almost no stars.
Well, almost without stars. It has a tiny fraction of the stars a galaxy of its massive size should normally have. It is basically 99% dark matter.
How do you even find a galaxy you can't see?
You look for the gravity. You see how its mass distorts the light of galaxies behind it, or how it physically pulls on things around it. But in terms of visible light, it's a ghost.
This challenges the whole standard model, doesn't it? We usually think gas falls into a dark matter halo, the gas gets dense, stars turn on, and the galaxy lights up.
Right, that's the standard progression. Here, the massive dark matter halo formed, but the lights just never turned on. Or maybe the gas was violently stripped away by the cluster environment before it could ignite. It suggests the universe might actually be full of these failed galaxies. Just massive, dark, silent structures drifting through space that we've never noticed because we only ever look for the light.
That is just haunting.
It really is. It implies that the visible universe, the billions of stars and galaxies we see in the Hubble and Webb images, might actually be the minority, the exception to the rule.
Add that to the jellyfish galaxy they just spotted 5 billion years after the Big Bang, way earlier than we thought possible. And the published plan to chase down that interstellar comet 3I Talus with the solar slingshot maneuver in 2035, the universe is just packed with mysteries right now. Which brings us to our final segment. The machinery that allows us to find all this stuff. The policy.
Yeah.
Because none of this happens without a very large checkbook.
The engine room of space exploration.
We had a massive scare recently, the 2025 and 2026 budget cycle. NASA science was looking at historic, devastating cuts.
It was incredibly bleak. We're talking about canceling flagship missions, firing thousands of specialized contractors. But the good news is Congress pulled it back from the brink. The FY 2026 budget largely restored near full funding for the Science Directorate.
So we take a victory lap.
Not quite. As Jack Carley and Casey Dreyer pointed out on Planetary Radio's Space Policy Edition, the oscillation itself is highly damaging. You can't just turn deep space science on and off like a faucet. When you threaten to fire everyone for 6 months, the talent leaves. They go to private tech companies, they go to finance. Even if the money magically comes back a year later, the brain drain has already happened.
It's the stop-start cost.
Exactly. You cannot plan a 10-year, multi-billion-dollar mission to Uranus if you don't know if you'll have a budget to pay your engineers next year. Stability is almost more important than the raw dollar amount.
There was a really interesting moral argument raised, too, referencing J.S. Johnson Schwartz, the idea that doing this science is actually a moral obligation.
I love this perspective. We so often justify space spending with spin-offs. We went to the moon and we got Teflon and GPS and better water filters, and that's all true and valuable. But Johnson Schwartz argues that curiosity is fundamental to being human. If we stop exploring, if we stop looking at the dark matter galaxies or studying the moon dust, we lose a vital part of our humanity. It's not just an economic investment, it's a cultural imperative.
And we definitely aren't the only culture doing it. China is surging right now. Space News today had a huge update on their capabilities.
It's a Shillong space plane.
The Divine Dragon.
It's back in orbit. Mission number 4. We don't know much because of the high secrecy, but it's doing complex orbital maneuvers, deploying sub-satellites, and landing autonomously. It's a direct competitor to the U.S. military's X-37B.
And they are testing scramjets now.
Project Cassowary-Vex. They are actively looking at hypersonic flight, the ability to fly through the upper atmosphere at Mach 5 and beyond, using Rocket Lab Electron launches to test it. It has obvious military applications, but it also fundamentally changes how you might get payloads to orbit in the future. Add to that their tests of reusable boosters for lunar missions, and they are moving incredibly fast.
It really feels like the board is being set for the next 50 years of human history.
It is. The U.S., China, the booming private sector. Everyone is positioning themselves right now for a permanent presence beyond Earth.
So let's wrap this up. We have covered a massive amount of ground today. We've gone from microscopic hydrogen isotopes in 50-year-old moon dust to the invisible structure of dark matter halos millions of light years away.
If I had to synthesize it all down into one core takeaway for the listener, I think the theme today is resilience and reality.
Unpack that for us.
Well, we are digging into the moon to find the resilience of information chemical data that survived billions of years of solar system chaos. We are seeing the resilience of the Artemis crew dealing with crushing delays and returning to quarantine. We're seeing the Voyager probe surviving out in the dark, turbulent edge of the system. But we are also facing the hard reality. Europa might be dead and sealed shut. Mars is punishingly hard. Budgets are incredibly fragile.
It's a maturing of the space age. It's not just planting flags and leaving footprints anymore. It's hard science, hard engineering, and really hard policy.
Exactly. We are moving out of the purely adventure phase and into the industry phase.
Yeah.
And industry is just inherently messy.
I want to leave you, the listener, with a final thought based on what we discussed today. We talked heavily about the quiet Europa theory, that the vast subsurface ocean might just be completely still and silent, cut off from the energy it needs. And we talked about the dark matter galaxy, a colossal galaxy with basically no shining stars.
Two very dark, very quiet concepts.
Right. So here's the provocation for you to think about. We spend so much time looking for Earth 2.0 or stars exactly like ours. We want the universe to be just like us, noisy, bright, wet, active. But what if the default mode of the universe is actually the dark? What if most oceans in the cosmos are just sealed shut and sterile? What if most galaxies are totally invisible?
Are we the rule? Or are we just the freak anomaly?
Exactly. Are we just the incredibly noisy neighbors in a very, very quiet cosmic library?
That is a genuinely chilling thought. But it does make our little blue marble seem even more incredibly precious.
It really does. So something for you to mull over while you look up at the sky tonight, and you really should look up. There are actually 6 planets visibly aligned in the sky this week. Go outside, take a look, and realize just how incredibly lucky we are to be on this loud, wet, bright blue rock.
Absolutely. Keep looking up.
Thanks for diving deep with us. We'll see you on the next mission.